Hello everyone, welcome to my second video. I'm Simon. Now you can see that the content in this video is not as I'm originally planned for my second video, but nonetheless, what I'm talking about in this video is an important part when we think about probability and statistics, namely the moment generating function of a particular kind of probability distribution. In this case, it's the moment generating function of the gamma distribution, which is then a quite important distribution in higher level of probability and statistics. And we are going to find out how the result of its moment generating function is being obtained. Roughly speaking, I would like to divide my following explanation and introduction into three parts. The first comes the definition of moment generating function and how does it do. Then follows by the gamma function. Basically, it's a kind of integral integrated from 0 to infinity with some nice properties of a particular function, the integral. And the final part, we are going to see how gamma function has been related with gamma distribution, and we are aiming to find out its MGF, the procedure of the derive of the result. We are going to see it in a more detailed way. So now let's begin on my first part. What is a moment generating function? Roughly speaking, moment generating function is a kind of systematic way of manipulate the nth moment to a particular kind of random variable, supposed to be x. So then these moments are expectation of x, expectation of x squared, and expectation of x cubed, and so on and so forth. We do the calculation by differentiate the moment generating function taken to be the expected value of e to the tx power and differentiate respect to t. Then take the result of the derivative at t equal to 0. If we conduct this process twice, we can then find out the mean value at the expectation of the x squared. And then we can do some other sorts of calculation which is proved to be useful, like we can calculate out the variance of a random variable, say x. We can then calculate the variance x by using these two figures. The formula is e to the x squared minus e to the x all squared. And it is exactly what the moment generating function plays its role in this case. And then we are going to talk about the gamma function, which, as I have explained previously, a special kind of integral. Sorry for that. Gamma function, a special kind of integral, starts from 0 to infinity with respect to a function written as x to the alpha times e to the minus x. The integral is integrated along x from 0 to infinity. If we conduct this procedure applying a method called integration by part, we can then find out the recurrence relationship of this fancy gamma function, namely gamma alpha plus 1 is equal to alpha times gamma alpha in bracket. And here it is just the the definition of the gamma function. The recurrence relationship it appears is just the unique point of this kind of function. And the final part, we are going to see how it is related with gamma distribution and find out the moment generating function of this specific kind of distribution. The probability density function is written down as follows. You can see that the gamma function is appeared on the denominator. Other things, there's not quite much to worry about. We are then going to find out the moment generating function of this kind of distribution. First, we just apply our definition on moment generating function. We can see that it is also an integral because gamma function distribution is a kind of continuous distribution. It is just the opposite side of another terminology called discrete probability distribution. When we talk about discrete, I mean, for example, you roll a dice. There are finitely many sample points, like 1, 2, 3, 4, 5, 6. These 6 sample points, they are discrete values. You cannot take any value between, say, 1 and 2. There does not exist such a figure for you to take out. But random distribution is just the values are taken in a range of intervals rather than discrete values. These are the main difference between these two types of distribution. And when we are considering the continuous random variable, the way to sum up is just to integral. And there's a reason why this result is proposed as a integral from 0 to infinity. Then what we are going to do is make a suitable substitution to make our calculation handy to proceed. We do as follows. We set u equal to 1 over beta minus t to the bracket times x. Oh, by the way, I should say that this row, I grouped together two similar terms, e to the tx and e to the minus 1 over beta times x. I group them together, these two terms together. So it takes the forms like that. I should stress on that. Sorry for that. Then it comes to our method of substitution. I have just told that let u be 1 over beta minus t, or in a bracket, times x. And then we do the normal procedures as if we are deal with integrals by substitution. Do the same procedures and be careful with the calculations. What we are supposed to be found is actually we have successfully substitute all the terms in our original integral related to x in some form of u, and inside the integral we construct another gamma function which can be eliminated or cancel out with the one already on the denominator. And this is our strategy on solving this or derive this result. And the final result is 1 over, in the bracket, 1 minus t times beta to the alpha's power. and that finishes our calculation on this useful result. And that also finishes this video. I shall stop here and see you on next video. Thank you very much. Goodbye.